Assalamualaikum. Boleh dengar ke?
Dengar, Prof, dengar.
Boleh dengar
Dengar
ke?
ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar. Dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar. Dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar. Dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar. Dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar. Dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar, Prof, dengar ya.
Okey. Tadi sebab bunyi tu takut tak clear.
Dengar ya.
Okey. Tadi sebab bunyi tu
Assalamualaikum and a very good morning everyone. My name is Fatin Zulaika and I am from the Faculty of Science UPM. Welcome to the Malaysia-Brunei International E-Mobility. For everyone's information, today's program is organized by the Faculty of Science Students Association, FASA, University Putra Malaysia, in collaboration with the Faculty of Science Student Body, FOSB, University Brunei Darussalam. As you can tell, I am very glad to be here today to start our very first agenda of the program, which is the virtual class session. The session will be about showing all of you how classes are conducted in both universities. It's a chance for us to see different approach to learning and discover various types of experience. I really hope we will all have a productive and enjoyable learning experience together. So let's begin with high spirits. During our first slot, We will be with Professor Dr. Zanaria Abdul Majid. Professor Zanaria is a lecturer at the Faculty of Science UPM, and her expertise is applied mathematics. She was the faculty's Deputy Dean of Research and Postgraduate, and she was also presented with multiple awards, namely Anugerah Persama 2019 and Anugerah Persama 2022 under the Malaysian Mathematical Science Society. Today, she will be teaching us a subject called numerical analysis with the topic ordinary differential equation, one-step method. Therefore, without further ado, give it up for Professor Zanaria.
Thank you very much for the introduction. Can everyone hear? Okay. Okay, so I'm glad today to participate in this activity. Okay, for our today class, later on I'm going to close my video because I'm scared that maybe it might interrupt our class. Okay, so for students as usual, okay, so I will prepare the Google form I have attached in the chat for you to register for our class today because it's very important for us to take the attendance. So I prepared the Google form. So for our students, please take your attendance. And also I have prepared for the learning activity today. Okay, so it's good each of you will download this learning activity because we're going to do it together, this activity. So please, okay, so download it and have it in your computer. Okay, so therefore we can do all the exercise together. Yeah, okay, so now we can start. Yeah, so I have to close the video. So I will attach the screen. Okay. Okay, can everyone see the slide that I share here? Can is it clear?
Yes, ma'am.
Okay, thank you very much. Okay, so usually in my class, I will prepare this learning activity for the online session to make sure that my students know what I'm going to deliver today and what what the students going to learn, yeah, for their classes today. Okay, so for today, this is the course MTH 3501 numerical analysis, and I will cover topic 9, that is ordinary differential equations, one-step method. And I am Prof. Dr. Zanaria Abdul Majid. Okay, so this is the module that I have prepared, and this is a duration of 2 hours online. And it's very important at the beginning of the lesson, okay, I will inform all of you the learning outcomes, okay, what you're going to learn today, okay. So at the end of this module, students are able to identify a one-step method, yeah, and then you also should be able to derive the Euler method using Taylor series. And then you also able to solve ordinary differential equation, that is ODE, using the Euler method that will be introduced to you in objective number 2. Okay, so this learning outcomes is very important. At least you can have a checklist of yourself. Okay, are you able to achieve all of these 3? But of course, in my teaching, I'm going to make sure that you are able to understand maybe through my example and also the exercise that I'm going to give you. And if you have any question, please, yeah, you just can ask me. Okay, and I try to answer any of the questions. Okay, before we start with this learning activity, I want to share with you. Oh, I thought I can. Okay, I want to share with you the slides. So I think I thought I can link it here. So it looks like I can't link, so I will stop the share. Okay, so I will open it again. Okay, so please wait for a while because it looks like I can't open it just now. So I will share with you. Okay, before we start, so this is something that I think I need to briefly explain to you. Revealing mysteries by numerical analysis. Okay, as we know that there's a lot of phenomena happen all around us. Okay, one of the example you can see that is the earthquake. Yeah, the earthquake can happen anytime. Are we aware of it? Are we alert of this phenomena? And also tsunami, it also can happen. Okay, in any place, but we as a human being or as a researcher, can we do something about this? At least we can give alert to the people out there what's going to happen. So this is all the phenomena that might happen, and there's many more actually. Yeah, so you can see that that's what happened in all over the world. Okay, so you can see that we encounter so many several problems that need to be analyzed and solved. Okay, we as a human being, we know that we have so many problems and we need to analyze and at least try to solve it. So in mathematics, so of course it's impossible to solve to exactitude real world problems. Yeah, of course we can't get exactly. For example, in mathematics, can we predict exactly when the earthquake going to happen? Of course, sometimes it's impossible, but we will try our best to approximate and when it can happen. Okay, so therefore, the idea of the solution of the problems will be very important for us. So how do we solve the problem? Okay, the problem around us. Of course, the first step is that the problem description, we describe the problem, okay? And then from there, a mathematician will construct a mathematical model. And from the mathematical model, then we can solve the solution of that mathematical model. And then when we solve, we will get the solution. So in this case, where is numerical analysis? Okay, numerical analysis is in the third step, where we're going to solve the given mathematical model and we're going to obtain the solution, and we will give the solution that we obtain, that means the approximate solution, to the right person that going to predict what going to happen from the problem that they have. So in this numerical analysis, where we study the algorithm, where from the algorithm, we will do the approximation, numerically, we approximate numerically the problems of the mathematical analysis, but it is in the form of differential equations. Okay, So as our today topic is ordinary differential questions. Well, it's quite related. And the numerical methods and techniques, okay, so there are many methods in numerical analysis and there's many techniques in numerical analysis in order to solve the problem that has been created by the researcher. So as you can see here, there's many more actually, yeah. But today you can see here we have this Euler method, yeah. So Euler method is what we're going to focus today, yeah, where we're going to solve for the ordinary differential equations. And the types of question, you can see that there's a lot of types of equation from the modeling that has been discovered by the researcher. Okay, it can be in the form of differential algebraic equations, it can be in the form of delay differential equations, in stochastic differential equations, in partial differential equations. So there are even in integral differential equations, so it can be in different form. Yeah, the mathematical model that has been construct, it can be in different form of mathematical model. So this is what numerical analysis we're going to solve. But for today, yeah, we're only going to focus for a very small, just a part of it that is ordinary differential equations. So why do we care? Yeah, okay, we care because differential equations describe almost everything in the world. Okay, even the researcher in the fluid dynamic area, they construct the modeling and the modeling in terms of partial differential equation, that is PDE, but they convert the partial differential equation into the boundary value problems. And the boundary value problem actually is in the form of differential equations. So you can see that everything in the world, even in physics, chemistry, engineering, and many more, is in the form of differential equation. So what is our goal? So our goal is for the field of numerical analysis is where we want to design an analysis of the techniques where we want to give the best approximation solution. That means the best and the most accurate solutions to the given problems, because the solution is very important, because from there the researcher or the person that want to predict something, it depends on the solutions that we're going to provide to the researcher. Many industries have problems which can potentially be formulated and solved using mathematics. And I'm not sure if you are aware of so many problems out there, even in industry. So they need mathematics to solve the problems. And maths connects with all areas and knows no bounds or constraint. In all areas, actually, mathematics exists. And industry will need all mathematicians in order to survive and grow. And also, there's somebody from the Exxon, the ex-president, saying that there's too few people recognize that the high technology celebrated today is essentially a mathematical technology. Okay, so this is one example I give to you. This is the earthquake problem, okay, where we want to measure how the earthquake induced vibration on the multi-story buildings. So you can see that this is mx double prime. That means this is a second order ODE. And there's a system of equations of second order ODE. So this is a real problem, but from the mathematical modeling, okay, they construct it in the form of the ordinary differential equations. This another example, okay, a flying object, where it also can be formed in the in terms of ordinary differential equations. And this is just a simple problem. Maybe later on, after you have learned of this class, you even can solve this problem using the Euler method. So hopefully that you have a clear idea of this, how useful the method that we're going to learn, because it's going to solve many of the existing problems outside. Yeah. Okay, so I'm going to stop the slide. So if you have any questions, anytime, you just can ask me. Okay, now we go back to our learning activity for today. So I just showed to you the intro for how useful the method that we're going to learn. Okay, first we go for task 1, introduction. What is ordinary differential equations? I think most of you, of course, you are mathematician. Yeah, so you are doing degree in mathematics. Yeah, so you should know what is ordinary differential equations, where the derivatives are taken with respect to only one variable. That is only one independent variable. Okay, if we have more than one variable, that is already partial differential equation. Yeah, but now we are going to handle the ODE, ordinary differential equation. So below is some of the examples. Okay, so you can see the example here. So you can see that the ODE can be represented in different forms. So you can see this can be y prime. It even can be in form of dy dx. Okay, so actually it's represent the same meaning, only different symbol. So y prime, that means that is the first order, although also dy dx also the first order. And we even have a higher order. So this is second order, d2y, dt2. Yeah, that is second order problem. Even it can be represented as y double prime. So, okay, so you can see that it can be in different symbol. But as a mathematician, we should know that although it's in different symbol, but it gives the same meaning. Yeah. Okay. So we go for the application. Okay. So this is the application that I just showed to you in the slide. Okay. Just to share with you again, where the ODE, okay, can also be in the modeling for the growth of the diseases. Yeah, even it can describe the movement of electricity, okay, even the motion of the pendulum, okay, and the law of cooling, and many more actually. Yeah. So I hope that you realize that what you're going to learn today is something that can solve the real problem. Yeah. Okay. So we go now. That is task 1. Okay. So now we go for task 2. As you can see in the topic just now, you can see that one-step method. Okay, so we have this topic is about ordinary differential equation, but we're going to solve using one-step method. Okay, what is one-step method? Okay, and why it is called as one-step method? Okay, the method is called as one-step method because the approximation for the mesh point, that means at the xi plus 1, involves information from only one of the previous mesh point. Okay, so if I draw the interval, okay, so we can have this is xi plus 1 and this is xi. So that means if we want to find the y at the I plus 1, okay, when we want to solve, we want to use the one-step method, we only need 1 point at the previous step. That means we only need yi at xi. So that's what it called as one-step method. There's also a method where it needs more than that. For example, it needs, here we might have xi minus 1. And here is yi minus 1. Okay, but for one-step method, in order to compute yi plus 1 at the xi plus 1, we only need 1 point, 1 previous mesh points. So that is why it called as one-step method. Okay, next topic, yeah, in topic 10, we're going to learn of multi-step method. That is multi-step method, but this is one-step method. Multi-step method, it involves more than 1 previous points. That means it might involve the xi and xi minus 1. That means it involves orally 2 mesh points. So that is multi-step method. But for today, okay, we're going to learn of one-step method that it involves only 1 mesh points. Okay, so for example, okay, this is Euler method. Okay, and also we have Hume's method that is from RK. RK is Runge-Kutta. Yeah, Runge-Kutta two-stage method. So these two example is one-step method. Okay, so maybe I just highlight it here. You look at the Euler method, why this is from the family of one-step method. Okay, you can see that this is the y at the xi plus 1. If you look on the right-hand side, we only need 1 previous point, that is yi at the xi. So that's why Euler method is one-step method. Okay, now we check for the Hume's method. Okay, look at Hume's method. Hume's method, two-stage because it has K1, it has K2. So that's why in this form, we know we call this Hume's method as Runge-Kutta two-stage method. When you look carefully, this is where we're going to compute the y, yeah, along the interval for the value of y at the point xi plus 1. And I think you can see very clear on the right-hand side, we only need 1 previous mesh points, okay, that is at yi. So this is why this Euler method and Hume method is in the family of one-step method. So hopefully, by this example, if I give to you, okay, any of the method and you are able to identify which of the method is in the family of one-step method. Yeah. Is there any questions, students? No questions, eh? Okay, if no question, okay, so I just continue. Okay, now I go for task 3. Euler method. Okay, the idea of this Euler method is actually it comes where we're going to form a tangent line in the that touch the curve. Okay, so now you look at this. This is actually, we can see that this is the curve. Okay, the curve for the maybe I can say that this is the exact solution. From the exact solution, that means we can plot the curve. You can see that it's a smooth curve. Okay, so what's the idea is that for the tangent, of course, when we start to compute, it start at the point x0, y0. Okay, when we start at x0, y0, so then we're going to find what is x1. So this is at the x0, and this is at the x1. Okay, what we're going to do is that we want to find what is the y1 at x1. Okay, what is the value of y1 at x1? So the idea is to draw a tangent line that will touch at the point x0, y0 in order to find the y1 at x1. Okay, so that's the idea. Okay, so hopefully you can get the brief idea of the Euler that related to the slope of the tangent line. Okay, so now I'm going to continue. Okay, so this is just the idea. At least you can see the visual of it. Okay, next we're going to derive the Euler method. Okay, so this is not the only way of derive the Euler method. Okay, so there are several other ways how to derive the Euler method. Okay, for example, we can use the Lagrange and do the integration. I hope you are familiar with Lagrange integration polynomial. Okay, if you are taking this class, you have learned it in the earlier chapter. And also you can use the forward difference method to derive the Euler method. Yeah. And also you can use the many other ways of idea, okay, that if you attempt to know, okay, you can explore on yourself the derivation for Euler method. But for today in our class, we're going to learn derivation of Euler method using Taylor expansion. I know that each of you are very familiar, should be very familiar with Taylor expansion, okay, because all of you already took calculus, okay, in your class. Yeah, you should have be familiar with Taylor series or Taylor expansion. Okay, so in this case, okay, so given this y prime equal the function f, where this is given the initial condition, and this is where we're going to solve the interval that is at a, b. Yeah, the x is between a and b, including a and b. Yeah. Okay, now we're going to expand using Taylor expansion. Okay, so when you look at a, yeah, each of you should be familiar of this Taylor expansion. Of course, I did not write so many terms. I just put the dot, dot, dot. Yeah. So I just put here up to order 2. Yeah, for the Taylor expansion. But I hope that you know if you want to extend, you can continue and have continue the Taylor expansion. Okay, so from there, what we're going to do is that we're going to let h. H is the step size. Okay, if I draw, okay, you can have here, you have the xj, you can have the xj plus 1, you can have here xj plus 2, and so on. So that means the difference between this point, it is known as h. That is a step size. That means we can choose the step size that we want to have. So we put it as the h. Okay, in numerical analysis, the h will represent as a step size. And then we also can obtain the h by using this formula. That means the difference between the b minus a, that means b minus a just now is the this interval. That means the x, yeah, the x is between a and b. Okay, so we also can get what's the value of age. Sometime in the question, it did not give us what is the value of the step size. So we have to find on our own. Or maybe in the example, it just give us the value n. N is how many subset that you want to have, you want to divide the interval. Yeah, you want to have the n as 10 or n as 20. So it depends on you. Okay. So if you have larger n, that means you will have smaller step size. Yeah. Okay. So there's two ways for you to find what's the age. You can find the difference between the two value of the x, or if you know what is the value of the n, so you can find the difference between the A and the B, and you divide with the n. Then you can find what is the step size. And then we're going to let x equal xj plus 1, and we may write y xj plus 1 equal yj plus 1. So this is, we want to make it simpler. Okay, so this yj plus 1 is the computed solution. Okay, so if we look at this Taylor expansion, okay, so you can see now the A will be represented in this form. Okay, now we look carefully. The x is equal xj plus 1. So that means this x will become xj plus 1. Okay, so we have y xj plus 1. The x is now equal xj plus 1. So I have y x at j plus 1. Okay, so therefore this is y xj plus 1. So that's why we may write as y at j plus 1 equal, okay, we make it simpler, y xj we write as yj plus, this is y prime. You can see y prime. But if you look carefully, okay, y prime is actually the f itself. This is the y prime. Yeah, this is the y prime. Okay, so the above is the y prime equal the f. Okay, so this is the y prime equal the f. Okay, so that's why here we will use y prime here, but we will change it to f. Okay, so we have the f, because f is as a function, so it must have two values of variable. So we have xj, yj. Okay, and then, okay, so this we just have it again. So x minus xj, but now our x is xj plus 1. Yeah, because we have let x equal xj plus 1. So now you can see that when xj plus 1 minus x, so all of these actually will become ish. Okay, from the above notation that we have identified. So therefore, we can write the Euler method, yeah, as yj plus 1 equal yj plus f at xj yj times ish. So ish is from the difference of xj plus 1 minus xj. Yeah, so this is the formula. So if you look here, from the Taylor expansion, we can increase the order as many as we want. But specific, if we want to derive the Euler method, we only will consider up to the first two terms only in order to get the Euler method. Okay, so the rest will be ignored and it will become the as the order of the method, or we call it as the big O. Okay, the big O. Okay, this I will cover later on, but not for today. Yeah, the big O, it will describe the error for the Euler method. Okay, so if you have questions, please ask. Okay, so this is actually a simple derivation for the Euler method. Okay, so for today, I purposely show for Euler method. So I'm not going to show for Runge-Kutta method. So it will be in our next class. Yeah, for the Runge-Kutta method. So today only I share with you, okay, derivation for the Euler method. If any of you interested, okay, you can explore on your own derivation for the Euler method using Lagrange, and then you have to take the integration. That will be very interesting. Yeah, you will get the Euler method, the same method, yeah, the same method, but is a different approach. Okay, so now we go for task 4. Okay, so task 4 is for me to show to you how can we solve this Euler method, how can we solve this given ODE using Euler method. Yeah, so you can see this from this example. We need to use Euler to solve y prime equal x square plus y square. Okay, so it's very clear this is first order ODE because this is y prime. So this is first order ODE. And then it gives us the initial condition. This is the initial condition. Okay, so we need to have the initial condition in order to start to solve using the Euler method. And then you can see that here it gives us the n equal 10 and h equal 0.1. Okay, so from the example, we need to have initial condition, and then we need to know what is the value of the h. If we don't have that information, it's very difficult for us to solve using Euler method. Yeah. Okay, so just a note. So we're going to solve within the interval 0 to 1. Okay, so when you look at here, okay, so this is the idea. Okay, I just draw the interval. Okay, so we will have, this is x 0. So we'll have here x1 and then x2, x3, and it can continue along the interval. Okay, so the first what we're going to do is that you look at this initial condition. Make sure that you know how to interpret it. Okay. Okay, I just want to change color. Okay, so you can see that y0 equals 0. So what does it mean? It means that this is x0. So that's why we have x0 equals 0. So this 0 is the value of y0. That's the first thing that you must make sure that you are clear from the given initial condition. Y0 equals 0. Okay, so therefore you can take x0 equals 0 and y0 equals 0. Yeah. Okay, so now here that means I will have my y0 here. And then I have my h, the h is 0.1. Okay, so now we're going to start, okay, but bear in mind because this n is equal 10, that means we are going to find 10 approximate solution. Yeah, That means it starts from y1 until y10, because the n is equal 10 and we have our age is 0.1. Yeah, so that means it's a good exercise. You keep on repeating and do the calculation. Okay, so we start. Yeah, so this is our first task. Okay, so we have our, so I want to find y1 at x1. Okay, and what is x1? Yeah, so x1 is equal x0 plus h. So x0 is 0. Okay, sorry, because this line so is quite slow. So 0 plus 0.1. Okay, so that's why our x1 is 0.1. Okay, so this x1 is 0.1. So we have the x1. Now we want to find y1. Okay, so we will use the Euler method. Okay, you can look at the formula. This is the formula of Euler method. We're going to let I equal 0. In the formula, we're going to let I equal 0. When I equal 0, we will have y1. Okay, I will have y1. Okay, I equal 0. I substitute into this Euler method. Yeah, so I have y1 equal y0 plus the f. I have x0, y0, and then times the h. Okay, so I just substitute by taking I equals 0 here. So hopefully that is clear for you. Okay, when we want to move, we need to look at the I. So we let I equal 0. So this is the formula that I have. Okay, so now when we look, this is y0. So as you can see, what is y0? Y0 is equal 0 from above. Okay, and then plus f x0 y0. So we substitute, this is 0 0 times the h is 0.1. Okay, so we have that. Okay, next we're going to find, okay, this is 0 plus, okay, so this is f0 0. What is f? F is actually the problem itself. This is the f. This is the f. The y prime, okay, the y prime, that means the question that be given to you for you to solve, that is the f. That means we have our f xy, that is the given y prime, and it is equal x square plus y square. Okay, so now you know which one is the f. The f is the y prime itself, the given question. Okay, so next we're going to solve. Okay, so this is the f. So I straightforward use. So this is x square from the f plus y square. So we have just 0 plus 0. So when we multiply, the answer is 0. Okay, so we have our y1 is 0. So therefore, I have my x1 and y1. The answer from my first step is that x1 is 0.1, but my y1 is 0. That's the first step. Okay, of course, we just obtained the value of y1 at x1. So now we can continue to find y2, because along the interval, we will continue to find what is x2. Yeah, as you can see here, we already obtained y1. Now we continue using the same step size h, that is 0.1, and we want to find y2 at x2. And we still going to use Euler method. Yeah. So we're going to repeat the same process, only that you have to be careful of your calculation. Okay, so now next, to find for the x2, to find the y2 at the x2, you will let I equal 1. When we let equal 1, you substitute into the Euler method above. Okay, so hopefully you have your learning activity with you, as I have attached in the chat. Yeah. Okay, so this is, we substitute I equal 1. So then we will replace with the value. So y1 is just the result that we obtained just now. Okay, so it is 0 plus f, x1 is 0.1, y1 is 0, times the h is 0.1. Okay, and then we continue and we solve for 0 plus. So this is from the y prime itself, from the f, where we have our f, yeah, where it is the y prime is equal x squared plus y squared. So that's why here we have 0.1 squared plus 0 squared. Then times 0.1, so this is the answer that we obtain, where y2 is equal 0.001. Okay, so we can write it here. So now we have x2, y2. So our x2 is 0.2 and our y2 is 0.001. Okay, so the same process also for x3. Okay, so I want you to try for at x3 to find y3. Please try it now. Okay, what's the value of y3 that you will get? Okay, students, I want you to try it now. Okay, so for this exercise, I will usually I will ask my students to attach in the WhatsApp group so I can see their work. But because we don't have the WhatsApp group, okay, so hopefully that you are with me and you can understand the knowledge that I try to deliver. Yeah. Okay, hopefully that you try to do it from the learning activity, because there's a space in the learning activity that I provide. Okay, maybe we can, yeah, we want to find, we have our x3. Our x3 is equal x2 plus h. Our x2 just now is 0.2 plus 0.1. So we will have here 0.3. Okay, so as usual, I'm going to take my I is equal 2. Okay, so please you can refer to the learning activity as I have attached. Okay, I equal 2. Okay, now we will have y3 equal y2 plus f x2 y2 times the h. Okay, Okay, maybe somebody can, what shall I substitute here? What is Y2 here? Y3 equal Y2. What's the value Y2 that we just obtained just now from our previous step? Okay, so we just need to look at our previous step. So Y2 is equal
0.001.
yes, 0.001. Okay, thank you for the answer. So F, so we have here, we just substitute X2. X2 is 0.2. Okay, so our Y2 is 0.001. And my age is 0.1. I also need to be careful. Sometimes, yeah, if any of you can see that I did my careless here, so just inform. Yeah, in case of sometime I write something wrong, yeah, please inform me. Yeah, okay. So now we want to find for Y3. So we're going to do the same process. So this is 0.001 plus, so the F we can refer to the Y prime, and this is 0.2 square plus 0.001 square. Then we multiply with 0.1. Okay. Please use your calculator. And what's the answer for Y3? Okay, for our class, you can bring your calculator, and even in your final exam also, even in your test also, you can bring your calculator. Okay, so anybody that has used your calculator, and can you get the answer for me?
0.005.
Okay, good. 0.0050001. Okay. Maybe if we want to take at 6 decimal places, so we have only 2, 4. Okay, so we would know 1. Yeah, depend on you. If you want your answer only at 6 decimal points, so your answer is 0.005000. Yeah, so you can continue. Can you do as exercise now to find Y4 for me?
Yes.
Okay, please do the calculation. Okay, here we have already obtained for X3 and Y3, and we get the answer is 0.3 and 0.005000. Okay, just stop there. And please, you can do this, and you can calculate on your own, and you should get your Y4. Okay, and your Y4 should be 0.01400, actually 0026 here. But if you want to get your answer at 6 decimal places, okay, so you can get your answer 0.0140003. This is at 6 decimal places. Okay, so it's up to you. Okay, so what's your answer? Okay, now hopefully everybody can get the answer for Y4. So you can continue until you finish Y10. Okay, now I have the table up here. Wow, it's very slow. Okay. Okay, so this is the answer that we obtain. Yeah, you calculate for at X 0.1, and then at 0.2, and at 0.3, and also 0.4 just now. So this is the answer that we obtain. Okay, and this is, okay, so I put this the exact, but not all problems has the exact value. Okay, Not all. That means, of course, as you know, when we solve the real problem, of course, there's no answer. If there's already an answer, of course, people won't need to use any method to solve the problem, right? So there's no, well, most of the problem, there's no exact value. You will be very lucky if you have the exact. But for the purpose of this example, I share with you the exact for the example 1 that we solved. Okay, so now you can see that I want to find, okay, I want to divide into another column where this the error. The error is the difference between the exact and the approximate solution. That is the, I call this SYJ. Okay, okay. Maybe now we just try to find the error, maybe not all, just a few of these result. Okay, so of course this is 0, the first one. At 0.1, the difference between the exact and the approximate solution. Okay, so this is 0.000333. Okay, at 0.2, the error is 0.01667. And then we continue for 0.3. This is 0.004003. Okay, then you can continue. Yeah, you can continue more. So this is 0.007356. Okay. So now you can see that we can see how accurate the result that has been produced by the Euler method. But this is only by using h equal 0.1. Yeah. So hopefully that I hope you are able to understand. And if there's any question, you just can ask me anytime. Well, usually if our class is 2 hours, I will have a break of 5 minutes. So I'm not sure if for our lesson today, do you want a break of 5 minutes, students? Or can I continue?
Continue.
Continue. Okay, so I just continue. Okay, if any of you want to have a break for 5 minutes, yeah, you can. Yeah, actually, during my exact class, I will give a break, yeah, for my students. Okay, now we continue. Example 2. Yeah, before I make a conclusion of something that related to the step size, we're going to do this exercise, the same problem as above. Yeah, the same initial condition, but now we have the n is equal 20. Compared to our first example, n is equal 10. Okay, so you can see that in this example 2, it did not give you what is the step size. Okay, but make sure that you remember, okay, in order to find the h, okay, h is equal the difference for the b minus a. So now is 1 minus 0. Yeah, this is the interval. Divide by 20. So we will have our step size that we're going to use in these problems is 0.05. Okay, so not all problem will give you the step size. Sometimes it just give you the n, and you should be able to find the step size. Okay, so we will repeat the same process, only that now at h equals 0.05. So this h, you can see that it is smaller compared to example 1. Okay, it is smaller compared to example 1. Okay, so it means that in order to find the result at the x 0.1, I need to compute 2 times. Yeah, because later on, I want you to see and we're going to compare the result that we just obtained from above, from example 1, and we're going to compare with the result that we obtained from example 2. Okay, and what conclusion that you can take. Okay, so now I'm going to do it together. Okay, each of you also. Okay, now from here I have my x0 is 0, my y0 is equal 0. Sorry, so the line is very slow. I'm writing, but it's not there. Okay. Okay, so we start with I want to find my x1. Okay, and my x1 is 0.05. Okay, hopefully that you still remember how did we get x1. Okay, x1 is equal x0 plus the h. Okay, from the interval, we have the x0 and we have the x1. So the h is 0.05. So x0 is 0, x1 is 0.05. Okay, so we will use the Euler method. So again, I'm going to take I equals 0. When I equals 0, I will have my y1 equal y0 plus h. Quite slow on the line. Y0 plus h f okay, so I'm going to do it. So hopefully that any of you that is still not clear, hopefully that you know how to solve this. So this is 0 plus the h is 0.05. So I have my f, this is 0, 0. So from here, I will get the answer is 0. So this is the same as the example 1. Okay, so I have the result is x1, y1, I have 0.05, this is 0. Okay, then I proceed to find y2. Okay, I want to find y2. Y2 is at x2. So this is x2. So this were 0.1. 0.1. Okay. Okay, I'm going to proceed with the calculation. Okay. So I have my x2, y2. So my x2 is 0.1 and I don't know what's the y2 yet. Okay. So I will let my I equal 1. Yeah, you can refer to the Euler method. Yeah, to find y1 is I equals 0. To find y2, we will let I equal 1. Okay, therefore I will have my y2 equal y1 plus h f of x1 y1. Okay, so now I will substitute. So this is 0. My y1 is 0 plus the h is 0.05. and I have my F. Okay, so the F is just now I obtained 0. Sorry, students, the lines is very slow. I'm writing, but it did not appear. Okay, so that's my F. Okay, so I will have now 0 plus 0.05. And so this F is the Y prime itself. So I'm using the same formula. So this should be 0.05 square plus 0 square. Okay, can somebody do the calculation for me using the calculator? So what should be the result for Y2? Anybody?
Zero point 0.000125.
Okay, thank you. 0.000125. Okay, good. Okay, so that's the Y2 that you obtain from X2 0.1. Okay, so now we have our X2, Y2, zero point 0.1, 0.00125. Okay, so now I want you to find the error for this answer. For this approximate solution, you look at the table, you look at the table above and find the error. What's the error for Y2 that we obtain using the age 0.05? Can somebody find me the error? The error is where you take the exact solution and you minus with the approximation. So what's the error? You look at the above table at the X 0.1. This is the answer. Okay. You can see the difference now. This is the exact for 0.1, but from our example 1, we use age, the step size is 0.1, and we get this answer. Now, these are the error. Okay, now, you take the exact and you minus with the answer that we just obtained from example 2. Anybody? What's the error?
Negative 0.000917.
Is it 917? 0 point? You compare with 0.1.
Okay, I think I got mistake.
It's okay. 0.00. Anybody? Zero.
Should we take the should we minus the exact value minus 0.1 or the exact value minus Y2?
Minus Y2 because that exact solution is the value for Y2. That exact is the answer for Y. So that means you take the Y at the X equals 0.1. At 0.1. So the error is actually when you look at the when you look at the table, error is exact minus approximate. Okay, sometimes we put this as absolute value. It's very important. That means the error should not be in negative. Sorry, I did not remind that just now. So there should be the absolute value. So here in this case, when you look at the table above, okay, so at 0.1, the exact is 0.000333 minus the approximate that we just obtained, 0. Oh, so slow. 0.00125.
Actually, Prof, the second Y2 in the bracket, it's missing another 0.
There should be another 0. Oh yeah, thank you very much. That means you are very alert. That's why I will always remind my student to check. There should be another 0 here. Yeah, thank you very much. Okay, good. Yeah, up here is already correct. This below I copied wrongly. So this is 0. Wait, the blue color. 0.0. That means I should have 3 0. Yeah. 0.000125. Then you should get the error is equal 0.000. Anybody?
208.
208, yes. Okay, so I'm glad that you can see some of the, that's why I always ask my students to look at, sometimes I said it something, but I wrote it wrongly. So it's good. Thank you for give me the feedback. Yeah. Okay, so this is the answer for the error. Okay, for Y2. Okay. You can continue to find Y3 and then you find Y4. Okay, you can continue to find Y3 and then Y4 because Y4 is actually at X4 equals 0.2. Then you can compare with example 1 that we already obtained for the approximate solution using the step size 0.1 and we obtain X2. But at example 1, because the H is 0.1, therefore 0.2 is at X2 and that is Y2. Yeah, for the value Y2. You can compare. Okay, now when you look at this, okay, I just do with you up to Y2. Just compare the result. You look at the error that you compare the error between example 1 using the step size 0.1 and we use the step size for example 2 is 0.05. What can you say of the error that we obtain here between the two examples for Y2? What can you say? Anybody? Just now from the table above, what's the error using H equals 0.1? Okay, This the error, right? Okay, 0.00333. This is when the age 0.1. But when we reduce the age to be 0.05, yeah, I think you can see that the error is smaller. This is 0.002. Previously, it is 0.0003. Okay, so you can see that it's reduced. Yeah, in numerical analysis, although it's a very small difference, but it's actually very important in numerical analysis. Yeah, although it's very small difference, but the result is very important for us in order to make a conclusion. Okay, so you can continue to find Y3 and Y4, and you can compare, and I think you can really see a big gap. Okay, at the value of X 0.2. You try to compare the approximate solution between example 1 and example 2, where the X is 0.2. You can see that there's a big difference for the error. Yeah. So now from here, okay, what's the conclusion that we can say when we use smaller values of H?
Smaller error.
Yeah, yes, you are right. When we use smaller value of H, we can get smaller error. That means, what does it mean, smaller error? That means the result that we obtain is much more accurate, yeah, compared to the when we use step size H 0.1. Okay, maybe I just give you here, maybe later on you can try your exercise. Okay, so for Y3, if you continue to find Y3, yeah, where X3 is 0.15. So I just give you the answer. Maybe you can do your calculation later on as exercise. So for Y3, you will get 0. Wow, so slow. 0. 0.000625. Okay, for Y3. When you continue for Y4, okay, you continue for Y4, you shall get your answer is 0.001750. Okay, so Y4 is where X4 is equal 0.2. Okay, then okay, I just show, maybe later on you will do the exercise. So the error, okay, where I take the exact, yeah, from the exact at the point 0.2, and I minus with this approximate solution. So the error is 0.000917. Okay, so you can do the exercise later on, and yeah, just hopefully my answer is correct. Yeah, I also do the calculation on my own, so hopefully you can get the same answer. Okay, so these are the errors for the Y4 at the point 0.2, 0.000917. Yeah, so this is, we use H equal 0.05. Okay, just to write it here, our error just now when we use age 0.1, no, not 0.1, 0.2. Yes, 0.1, yes. And age 0.1, yeah, at the point 0.2, 0.2. So the error, you can refer to the above table, yeah, where we use, this is example 1, yeah. This is example 2. Okay, compared to the error is 0.0026667. Okay, I think you can see this is when age 0.1, you can see that it is at up to 2 decimal places here. Yeah, but here is even smaller. Okay, when we use age 0.05. So you can see that from this conclusion, okay, when we what we can say from this conclusion is that when we use smaller value of age, we can get more accurate result. Yeah, and of course, as a researcher, we want better result. Better result, that means it's more accurate. Yeah. Okay, so this is for the Euler method. So hopefully that at this step, we have achieved objective 1, and then we have also achieved objective 2, and also we have achieved objective 3. Yeah, for you to be able to identify the one-step method, and then also you are able to do the derivation of the Euler method using the Taylor expansion. And then also the most important is for you to be able to use the method to solve the ordinary differential questions. Yeah. So until this task, hopefully that you understand. Okay, I'm going to proceed. Okay, if you have no question, if there's any question that you would like to ask students up to this example 2. This example 2 is actually our task 4. Yeah, our task 4. If there any steps that you are not clear, you can ask me. Okay, so maybe there's no question. Okay, maybe later on, yeah, you can ask me questions. Okay, so now in task 5, okay, I'm going to show you the algorithm of the Euler method. Because in numerical analysis, of course, in example 1, example 2 is where I show to you, we still can do the hand calculation. But sometimes when the interval is very large and we have a very small step size, and because some of us would like to get a very accurate answer, it will be very tedious to do the hand calculation. Okay, and we have to proceed with the programming. That means this is the algorithm of the Euler method. So from this algorithm, if you have knowledge in C programming, in C++ programming, or even if you have knowledge in Java, you can do the program. Okay, you can do the program and you can get the answer. Yeah, of course, the basic of the hand calculation, as we have done in example 1, example 2, that is very important. Yeah, then from that knowledge, you are able to construct a C program, okay, through this algorithm of this Euler method. So you can see that, okay, I just go through very fast. Okay, so this is where this algorithm is only to solve for the okay, this is, you can see that it called as IVP. Sometimes the ordinary differential equation, it is called as initial value problem, yeah, or sometimes known as IVP. Okay, so this is all that we need to have the problem itself, the y prime, the interval, the initial condition, and then how many space or equally spaced numbers that we need to have, or how many times we want to divide the interval, okay, from A to B. So that also need to be identified. Okay, then this is the value that we're going need to input, and then this are all the outputs, of course, the approximation. So you can see that here from this algorithm, the first step is that for us to identify what is the age, and then initial condition, and then you can see that here the W is actually the Y0. Yeah, that's the step 1. Then step 2, you can see that there's a loop. Here you can use the for loop, but actually you have learned also you can use the while loop, or you can use the do while loop. It's up to you. Some students, they prefer to do the for loop, yeah, as you have learned in the programming language. Okay, so the loop from I to N, that means it will go from step to step to do the calculation using the Euler method. So this is, you can see very clear, this is of course the formula of the Euler method. Yeah. And then of course it need to increase the value of the t. This value of t actually the value for the x. Yeah. So for the next x, then it will do the calculation. Yes, so the loop will be repeat until the end of the interval. So this is the algorithm. Yeah. So each of us need to understand the algorithm in order for you to be able to write the programming code. Okay, when you are able to understand the algorithm, then you can construct the coding. Yeah. So what we have done from this algorithm is the basic steps that we have done in example 1 and example 2. Yeah. Okay, now next we go to task 6. Okay, in this task 6, okay, I want you to look at this figure that I have it here. There are 3 lines here. Okay. The black line, that is the exact solution. The red line, that is the solution from the Euler method, but using h equals 0.75. And then the blue line is the solutions from Euler. We use the h is 1.0. Okay, can I get a feedback from you when you look at this figure? What happened to the Euler approximate solution, or anything that you can give your conclusion, or you can describe something from this figure that I have here in our learning activity? What happened to this solution by Euler?
More accurate, I think.
More accurate? Why you
More
say
accurate.
more what?
More accurate if we reduce the h.
Okay, okay, that's very good. That's very good. You can see very clear. From the blue line, there's a big gap. Yeah, there's a big gap with the exact. Okay, you can see there's a big gap, but as we reduce the age 0.75, we can see that the curve is the gap between the curve has been reduced. Okay, that's very good. Okay, what else? Anything, what else that you can see? Anybody? I just want to hear your voice. Maybe another person would like to try anything. It doesn't matter if it's wrong or what, because in our class, it's something that we want to discuss. What can you see? What can you say from this figure? Anybody else want to try?
The higher the step size, the more it fluctuates.
Again, the higher the step size.
The higher the step size, the more the graph fluctuates.
Okay, that means we can see that it's oscillate. It's go up and down, yes. Okay, that's a good try. Very good. Thank you. Okay, so you can see that when we use Euler method to solve this problem, we don't know what's the problem. Yeah, doesn't matter what's the problem. Yeah, you can see that when the step size is larger, the result is oscillates. That means it go up and down. So something is wrong. That means it's not approaching the solution. Okay, but when we choose smaller step size, then it's improved, it's getting better. Yeah, okay, so this is very important. Actually, this is very important because of course, all the real problems, there's no exact solution. Okay, only in example 1, example 2, I just give you the exact solution for you. At least you can see how good you approximate from the Euler method, because it happened through my experience. Okay, when I was in one of the exhibition at Kuala Lumpur, I present my research in the exhibition, and then there's one student or maybe one researcher came and asked me, saying that he is in engineering, he is in the area of engineering, doing research in engineering, and he said that he got he tried one of the method available in, if I'm not mistaken, is in MATLAB. I think, if I'm not mistaken, he used one of the software and just use any method in the available software to solve the problem that he has obtained from his research. That means he has construct his own model and he want to solve it. But he asked me why the result he obtained is oscillate. That means the result going up and down. It's not smooth. Okay. Usually when we solve using numerical method, the result should be smooth. Okay. As we can see that the black line, that is the exact solution. You can see that it's very smooth. Yeah, very smooth the line. Very smooth the line. But what happened when we use Euler method? Okay, so now, in this case, I just advise to that researcher that when it's oscillate, the result that he obtained oscillate, number one, maybe he has used the wrong method, number one. Number two, maybe he needs to reduce the step size. Go for smaller step size. That is our advice. Maybe later on you also can give your advice. If somebody from other area get this answer, you can also give the advice where you can advise for the researcher to use smaller h, and then they won't get the oscillate graph. Okay. And then number 3, why is this happen? It also might be because of the model that they have created, and from that model they have in the form of the ODE, and it is a stiff problem. It is a stiff problem. Okay, so as the example 1, example 2 that we did just now, that is a non-stiff problem. Okay, it is a non-stiff problem. A non-stiff problem is very easy to solve. It won't have a problem like a stiff problem. Okay, not all numerical method can solve a stiff problem. Yeah, but for Euler method, we can solve the stiff problem, but we need to reduce to a very smaller h. Then we can get a good answer. That's the things that we need to be careful. Yeah, when we solve a problem. Yeah, so hopefully that when you look at your, for example, you are given any problem, and then you solve using Euler method or any numerical method, and then you plot the answer. Okay, you plot the answer maybe in Excel, and you can see that it's oscillate. That means it's going up and down, up and down. So what happened? Yeah, because we should get a smooth graph. A smooth graph, that means the method that you choose is able to solve the problem. Okay, so what you can do, so I mentioned to you just now, number 1, you can reduce the step size. So therefore, the result will be better, and you should be able to get a smooth curve. So you can see that now using Euler method, you look at the red line. The red line is getting better, but if you choose smaller h, maybe you choose h to be 0.01, for example. So hopefully that it can get the same curve, that means as the exact solution, not oscillate anymore. Yeah. So these are all the things that you need to be careful. Yeah, because it depends on the type of problem. Yeah, it can be stiff or it can be non-stiff. Okay, for these two problems, stiff and non-stiff, actually it's not in the syllabus. So I just mentioned it here because if any of you interested, it will be highlight in advanced numerical analysis. Yeah, but not for numerical analysis. This is 3501. So we will go more deeper in 45, MTH 4501. If there's any questions, anything that you would like to ask regarding this figure, students? Okay, so what I can say also is that the Euler method can be numerically unstable. It can happen. Okay, So that's why you can see that it's oscillate, yeah, when we plot the graph, because it can happen. The Euler method can be numerically unstable, but we can avoid that by taking smaller step size. Okay. Okay, now there's an exercise here that I would like you to do. Yeah, from what we have learned above, from example 1, example 2, there's one example. And if you have do the example, you just can email to me anytime. Okay, I'm going to give you my email. So it is student prof Zana @gmail.com. Okay. Okay, before you do this exercise, okay, just to highlight to you regarding this problem. Yeah, because through my experience, some of my students, they can easily make mistake. Yeah, because of from this initial condition. From example 1 and example 2, as you remember, the interval is from 0 to 1. Yeah, but now for this exercise is from 1 to 2. That's why the initial condition is start at 1. Because the A is 1, the B is 2. Okay, so from the initial condition, we have y1 equal 2. You have to be careful. So from this information, that means we have now x0 is equal 1. Okay, y0 is equal 2. Okay, because some students, because of the example, sometimes they confuse and they still take x0 equals 0. You have to be careful from the given initial condition. Don't make this careless mistake. Yeah. So here x0 is equal 1, y0 is equal 2. Yeah. From our previous, we have what's the question? Y0 equal, let me look. Y0 equal 0. From the previous example. So your x0 is 0 and what your y0 is 0. But now, the initial condition given to us, y, yeah, y0 is 2, x0 is 1. Yeah, and then the steps is the same. The step is the same as what we have done in example 1 and example 2. Yeah, so each of you can do this exercise and email to me. Yeah, this email, and I will check and I will reply back to you. Yeah, so now is 10 more minutes to 11. Yeah, so I know that some of you have your next class at 11. Yeah, so I'm about to stop now unless you have questions from what I have delivered today. Any questions, students?
No, very clear.
No question. Okay, thank you very much. So hopefully you will do this exercise and email to me before our next class because it's good. So therefore I can inform to you, maybe there's a few steps that you make a mistake, so we can avoid the mistake earlier. Yeah, before we go for the next method. Yeah, next method will be the Runga-Kutta method that we're going to solve because that is one of the one-step method. Okay, so thank you very much and have a nice day, everyone. Hopefully that you take attendance for our class today. Yeah. So thank you.
Thank you, Prof.
Thank you, Professor Zanaria, for the informative sharing for this morning session. Hopefully, all the knowledge shared will be beneficial to us all. I would like to request all participants to turn on their cameras on, and let's have a little photography session. Okay, I hope technical team already ready. Okay, on me. 1, 2, 3, smile. Okay, once again. 1, 2, 3, and smile. All right. We are now done with our first slot of the virtual class session. We are now taking a break and we'll be back again with the second slot at 2 p.m. with another special panel. Before you leave, for UPM students, don't forget to record your attendance by scanning the QR code displayed to claim your merits. Don't forget to stay tuned and see you later. Goodbye and take care.
Bye, everyone. Thank you.
Thank you, Prof.